Okay, now we will work out some sample problems of how to find limits analytically. We'll start with 14 from the book. One moment, please. There we go. So, 14. The limit as x approaches, it's always the beginning of a limit, -3 of 2 over x plus 2. So, like I said, we're really setting ourselves up so that we can take this number that it's approaching and put it into what I like to call a nice function. Just directly substitute it, and if everything works out, then great. So let's try that. 2 over, we do -3 plus 2, that's going to be, well, we can't really, well, we could say it equals 2 over -3 plus 2, that's 2 over -1, and that's 2. So, the limit as x approaches -3 of this function is 2, right? Because this function we know is going to, at least in parts of it, be nice and connected. Continuous is the word we use in calculus. And at some point, we're going to come along to, maybe this is x equals 2 on the graph, and we could just, or no, this should be -3. Yeah, that's fine. Let's just say that's -3, not 2. So as x approaches -3, what's the limit? Well, there's a dot, right? There's a point on the graph right here at -3, and its limit is gonna be that, from the right and from the left, we're gonna be approaching the point that's actually on the graph that we could find by just putting -3 into the function. Okay, let's give another one a try. 25. F of x equals 4 minus x squared. G of x equals, where are we looking here? The square root of x plus 1. And part A says find the limit as x approaches 1, an arrow, of f of x. And instead of writing f of x like they've written it, we're going to write the actual function f of x, 4 minus x squared. Alright. Always try direct substitution. That's your best friend. If he works, then that's great, and if he betrays you, you have to find some other way to go. So put in a 1 here. 1 squared is 1. 4 minus 1 is 3. Great. Part B. The limit as x approaches 3 of g of x. Oh, you know what? I did what I didn't want to do. Erase that and actually write in the function. Function the square root of x plus 1. Put in a 3. 3 plus 1 is 4. Square root of 4, 2. Alright, I'm waiting for the trick here. This seems too easy. The limit as x approaches 1 of g of f of x. Aha. Okay. Now, we have this theorem that tells us that this would be the same as if we just did g of the limit as x approaches 1 of f of x. Okay? Alright, good. So, now let's do this part right here. What's the limit as x approaches 1 of f of x? Well, we just did that. The limit as x approaches 1 of f of x is 3. So we've got g of 3. And the limit part is over. Now we revert back to stuff we've been doing for years. we evaluated the limit inside here. Now we say, what's g of 3? Well, essentially we did that here. We did plug in 3 here, and so the result would be 2. Okay, so we're just applying that theorem, putting the limit inside that function g. Take the limit of f of x and evaluate g at that point. Limit as x approaches 5 pi over 3 of cosine of x. Alright, so I'm going to try direct substitution. And I know it's going to work because I know the cosine of x is a nice continuous, everywhere continuous function. There's no holes, no vertical asymptotes, no nothing. So I know it's just going to work to put in 5 pi over 3. They're just giving us an example of a trig function. So what's the cosine of 5 pi over 3? Maybe this is just a good little review. Just for me, I'm just drawing you what's in my head. I'm thinking here's 1 pi over 3. No, here's 1 pi over 3. That would be pi over 6. Pi over 3, 2, pi over 3, 3, 4, 5. 5 pi over 3, and I know that this is going to be 1/2, comma, negative root 2 over 2. And the cosine is going to be this guy here, so this is 1/2. Alright. Number 44. So we've got f of x is given to be x over x squared minus x. Here's a graph of said function. The vertical asymptote at 1. Swooping down kind of like this. Like this. And then we see right here is this hole. And continues on. This would be 1, negative 1 right there. This right there's 2, and so on. So just looking at the picture, it looks like we're supposed to be able to figure this out. Let's see. It says use the graph to determine the limit visually. If it exists, write a simpler function that agrees with the given function at all but one point. That's what we're going to go after. So we'll do a and b first. The limit as x approaches 1 of f of x. So here's f of x. The limit as x approaches 1. It doesn't exist. It's not there, right? It's shooting off in this direction and in this direction. So just by the fact they're going in different directions, we know they're not going to approach the same value. Even though in reality they don't approach any value because they go off to infinity and negative infinity. So does not exist. B. The limit as x approaches 0 of f of x. As x approaches 0, what's the limit? Well, this function does not exist. It's not defined at x equals 0, but the limit does exist. It approaches from the right and from the left. It approaches the same value. What is that value? It's negative 1. Now it says write a simpler function that agrees at every point but this point right here. Okay. How do we do that? Well, it's just a simple cancellation, right? This thing right here, if it brings up in your mind another function, 1 over x. It looks a lot like 1 over x, slightly modified, but it looks a lot like 1 over x. So why is that happening? Let's take the function. And I notice all these x's. Look what we can do here. Factor out an x. If I multiply this x through, I would get exactly the denominator here. But see what we have here is this cancellation. We have 1 over x, right? It looks a lot like 1 over x, but slightly different with a minus 1 there. Right, moves to the right one. So this function is exactly like this function, except this function does not have a hole. at 0, right? It just has a vertical asymptote at 1. So, though this function is not identical to this function, it is identical at all but one point. It agrees at all but one point. So if we were to graph this graph, let's say, this is the red one, this one would come along, and instead of getting scared and blowing up, it goes right through there with no problem. Right? So they both agree at all but one point. Number 46. The limit as x approaches -1, 2x squared minus x minus 3 x plus 1. Okay. Alright, so this is the same as the one we just did, except for they don't give us a graph. So let's put in a -1 and see what happens. -1, if we directly substitute like we like to do, we get a 0 in the denominator, so that's no good. So what can we do about it? So remember, if we can rewrite this function slightly using most often cancellation, then we can find this new function that agrees at all but one point. And then that new function that agrees at all but one point is going to be all filled in with no holes. And then we can just directly substitute into that function. And since this and the new simpler function will have the same limit, we can use direct substitution with the simpler function to find the limit of the original function. And how do we do that? Well, we're going to factor this guy. You can tell that factoring is probably what they want you to go for. It's kind of funny to do problems out of the book like this. They're all set up nice, and you can kind of guess what they want you to do and what they're trying to kind of test you on. So since I know that I'm going to factor this, because it's a polynomial, and since I know I'm looking for a simpler function, and by that I mean we're looking for something to cancel out, I can probably guess that since there's an x plus 1 in the denominator, there will be a factor of x plus 1 when I factor this out. Okay, which leaves 2x. Gotta have the 2x for 2x squared. And now we need a -3, so all that's left is a -3. Let's see if that worked. 1 times 2x is 2x. -3 times x is -3x. You add those together, you get a -x. Okay, and we get to cancel these out. And I want to bring to your attention that I have put an equal sign here, but I am equating the limits of these functions, not the functions themselves. These functions are different. They're not identical functions. Remember, they agree at all but one point, so they couldn't be equal functions. But the limits are the same. So, having said that, you might not care, but I can't help you. The limit as x approaches -1. Now we're going to try and directly substitute. This is gone, this is gone, this is just a 1, this is just a 1, so this is all that's left. Put in a -1, 2 times -1 is -2, minus 3, -5. There's the limit. We used factoring of the polynomial and cancellation together in concert to cancel something out, so we could find that limit. Number 52, the limit as x approaches 4 of x squared minus 5x plus 4 x squared minus 2x minus 8. Okay, what do you think is going to happen when we try and put 4 in here? It couldn't have been as easy as just plugging numbers into functions forever, right? So we put a 4 in here. Let's just check. 16 minus 8. 2 times 4 is 8, and minus 8. 16 minus 8 is 8. Minus 8 is 0. 0 in the denominator is a big no-no. So let's fix that. what do you think we'll use? Probably, I would say, since they're polynomials, since we're looking for a simpler function, I'd say we're going to use factoring. So let's factor the numerator and denominator. We all know this. I'm going to throw a couple x's here. I'm looking for a -5 to be added, a +4 to multiply, and I'm going to need two negatives, right? Negative times negative is positive, add to make a negative, and 1 and 4. There we go. Let's try this one. X and an x, multiply to make negative, add to make negative. We got a positive and a negative, and I'd say it's a -4 and a +2. So look what happened here. Good. So now we've got the simpler function x minus 1 over x plus 2. This is as nice as it's gonna get. And now we try 4. Put the 4 into, notice that this factor over here was our problem. That was the culprit. He was hiding out in here before, but now he's exposed, and we can see that when we plugged 4 into here, it was this factor that was the problem. 4 minus 4 is 0, right? But now it's been eliminated. So anyway, we put a 4 in there. X, that's 4 minus 1, that's 3. 4 minus 1 is 3. And 4 plus 2 is 6. That'd be 1/2. The limit is 1/2. That was pretty cool. Right, number 56. Okay, so we've got the square root guy here, and that's what we're looking at. So let's try direct substitution. What do you know? 3 minus 3 is 0. That's no good. Okay, so what I've been doing is factoring. This is not, I'm not going to factor this, right? I don't have time for this. I've got important things to do. I have a life to lead. So what we're going to use instead is, let's get rid of this ridiculousness, this square root. And one way we can do that, and the way we'll probably always do it because it works so nicely, is I'm just going to take almost exactly the same thing, but instead of a negative, it's a positive. That's called the conjugate, right? I got a something minus a something. If I write the same something plus the same other something, that's called the conjugate. And we must do that in the numerator and denominator, of course. So this is going to be, and I'm just multiplying it by 1, right? This is 1, so I'm not changing anything right now. I'm not changing the function at all. So FOIL, right? X squared of x plus 1 times the square root of x plus 1 would just be x plus 1. And notice when we multiply 2, positive 2, times this square root, and negative 2 times the identical square root, they cancel each other out when we add them together. And what's left is a -4 over, let's just leave it the way it looks, let's not distribute this one, x minus 3 times the square root of x plus 1 plus 2. Let's see where it goes from here. Well, this is going to be x plus 1 minus 4, that's x minus 3 over x minus 3 times the square root of x plus 1 plus 2. X minus 3 cancels x minus 3. This is a much simpler limit. We take a 3, we put it in here. Right, the numerator is going to be 1. 3 plus 1 is 4. Square root of 4 is 2. 2 plus 2 is 4. 1/4. How exhilarating was that? Okay. That wraps it up for finding limits analytically with these problems that get thrown in there having 0 in the denominator. So I hope that was helpful.